Welcome back to the lab. We're back with part 2 because today we're going to level up our circuit analysis skills with some superposition and resistor networks. It's going to be awesome. If you missed our previous video, I definitely recommend checking that out first. It lays some great framework for resistor combination and voltage in general, which is very important for what we're going to be doing today. If you think that you already understand those concepts, great. Just dive right in. But I will say that it was pretty fantastic. You guys are awesome. You pointed out that I was drawing my voltage sources upside down, so like positive on the positive side, negative on the negative side. So today I will be fixing that problem by using a different voltage source symbol. Not because I don't like the other one, but man, that's so ingrained in my mind, I don't think I could flip it if I tried. But anyways, like I just alluded to, we're working with voltage and ideal resistors again today, but things are going to get a little bit messier. Things are going to get a little more complex. We're going to throw multiple voltage sources into the same resistor network. So we've got two different sources of current, and we're going to figure out a way to work with that and combine them. It's going to be awesome. So let's dive in. Excellent. And then our task is to find V4. Today we're going to be applying a theory. And this theory is known as superposition. Superposition is a general way to apply our basic knowledge of V equals I times R, or Ohm's law, to evaluate one of these sources at a time and then continue. Okay? And basically the idea is we want to isolate this circuit to only consider one piece of it at a time. So I'm going to draw this circuit again, but with only V1 considered. In order to do that with the theory of superposition, that means that we are assuming that the other voltage source is applying no voltage. If there's no voltage across V2, that means it's effectively a short circuit. So it will look like it has disappeared from the system. So now we're going to apply another theory that we talked about last week, the parallel combination of resistors. And we're going to combine these two resistors in parallel to find Req. So it's 100 ohms in parallel with 1 kilo ohm, applying the theory of 1 over, we went over it last week. We're going to be combining these two in parallel and adding on the 1 kilo ohm resistor. So 1000 plus 101 kilo ohm in parallel is 1090.9 ohms. So basically, if we would draw this again, basically what I'm saying is these are the same thing. As far as that voltage source is concerned, that's the equivalent. These are equivalent. So what do we do to translate this into our final answer? All right, we're looking for node 4. And we know that there is current flowing. We know that the parallel combination of these two is 90.9 ohms. We know that this total effective resistance is 1090.9 ohms. So we can use voltage, in this case, at node 4, is equal to the current flowing through these two resistors in parallel, which is 3.7 odd milliamps, and multiply that by our 90.9 ohms, or 0.33 volts. Okay, but that's not our final answer. That's 1/2, right? We were only looking at this 4-volt source. What about the other one? Yeah, that's fair. That's fair. So let's consider that. let's do the other voltage source. Let's draw this circuit from the other voltage source's perspective. We've got a 1 kilo ohm resistor. We've got a 100 ohm resistor. We've got node 4. And we've got another 1 kilo ohm resistor. And now you might be looking at yourself and you might be looking at this and saying, wow, that looks very similar. Huh. That does look very similar. In fact, it's almost exactly the same. Our equivalent resistance, this in series plus these two in parallel, it's the same exact solution. It's the same problem. So it's the same. And now I2, which is the current flowing out of V2 into that resistor network. Right, we get 10 volts divided by the equivalent resistance. That's basically 9 milliamps. Now we're going to take this and we're going to do the same thing, right? So if we combine these two in parallel, we get 90.9 ohms. If we have one current passing through 90.9 ohms, we know that's the voltage at node 4. Okay? So we're going to do that same exact thing. So this is the second part of that voltage. And we take I2 times 90.9 ohms. Great. Now what, right? We've got this voltage solved from this half of the circuit. We've got this voltage solved from that half of the circuit. What do? Well, we combine them. Don't trust me? Put it in an LC Spice. I might have made a math error. Hopefully not. But yeah. There it is. Right. We took a more complex circuit that has two sources of current. We evaluated them one piece at a time, combined them through superposition, and there you go. We got a pretty straightforward solution that didn't really require advanced techniques. Now, if you've got 15 voltage sources and a bunch of current sources and you try to apply superposition, you'll find that you spend quite a long time evaluating the system, and if I'm being honest, when things start to get more complex, this starts to break down a little. Like, you can't use superposition for everything, but it's like a good stopgap tool for me. It's not the most advanced analysis tool, but I think it can get a job done in a pinch. Speaking of superposition, I want to break this down. We just applied it, but I didn't really explain it first. Now, I'm trying a little flip from our last one where I explained it first, then applied it. So we applied it first, now we're going to explain it. So for superposition, when we're evaluating V1, all other voltage sources are analyzed as if they were a short circuit. So there's 0 volts across it, or V equals 0. And all other current sources become an open circuit. So current equals 0, right? Basically, we're eliminating every other source from the circuit. Current sources have no effect. Voltage sources have no effect. And we do that through this method. And that's really the core of it, right? And then you add together all the pieces. It's really not so complex. Because once we get rid of all the other sources, once we simplify the system such that there's only one source, it becomes trivial to analyze the network. Okay. Well, I still think this was fairly simple. I mean, we're getting there. We're ramping up the complexity. We're getting there. So I want to try to break this down into something that's going to look a lot more similar to our comparator problem. It's simplified, but it's very similar. Okay? And what we're going to do is we're going to put a voltage source over here. But we don't know what that voltage is. Wow. That is not my cleanest I've ever drawn a circuit, but that's okay. Hopefully you can follow along. Basically what we've got is we've got a 2-volt source over here, a 0.2 volt source here. There's a resistor network combining them together. And then from this voltage, there's a secondary resistor network that's kind of like in parallel with that one, kind of hanging off on the side. And we know that the end effect of this unknown voltage plus this known stuff results in 1 volt being present at that node. Wow. That's a little crazier, but this is also very similar to some pretty real applications. Like, let's say you've got some kind of switch mode power supply controller or some kind of internal compensation something. Ooh, getting mad, I'm throwing things. Threw my pen. Anyways, so you got some kind of compensation network and some external feedback that you're dividing down a voltage source, say a critical something that you want to set a comparator threshold for, and you know that threshold's going to be 1 volt, or a switch mode power supply controller that has a feedback voltage of 1 volt nominally. Hey, this looks a little more applicable, okay? So yeah, it's more complicated, but it's also pretty cool. So let's try to break this down. Oof. Where to start? Let's get started with this. I think let's start by simplifying the circuit. Yeah, that seems like a good place to start, because it's like if we want to start at this voltage or that voltage or that voltage, man, it just feels so complex. So let's get started. We are going to start by evaluating V2. We know that's equal to 0.2 volts. Then we know there's a 10 ohm resistor. And we know that there's a 2 kilo ohm resistor. Okay, then what do we have over here? Over here, we've got this parallel combination, because that's 0 volts, right? That's a short circuit. So these two are in parallel. This is R1 parallel with R2, or 166.67 ohms. Okay. Now what? Okay, we've got another resistor here. We've got 100 ohms. Yep. Just making sure I'm drawing that right. Yep, we got 100 ohms. And in parallel, we've got 1 kilo ohm. So just to show you what I've got here, right? V3 is represented as a 0 volt source. V1 is represented as a 0 volt source. We've put those two in parallel to build this network. These two are now in parallel to build that network. I drew it a little differently. I combined one of them. I should be more consistent. Sorry about that. So then we got R6, R3. Everything else that has not been combined still appears here. Okay, so we're going to call that 2,166 ohms. We're going to combine those two in series. And then we have this parallel combination of 100 and 1K. And if you remember back to our previous problem, we already solved this. We know that that is 90.9 ohms. Okay, so I'm going to come down here and I'm going to say that is equal to 90.9 ohms. And never forget your ground reference. It's very important. Okay. So if that's really what we have, I'm seeing this network over here in parallel with this network over here, right? Like we can take this and plop it over there and it would look very much in parallel. So let's combine that. Now we've got 2166 ohms in parallel with 90.9 ohms. And we get an REQ of 87.25 ohms. Okay, let's draw this again. Now we have V2, 0.2 volts. Got a 10 ohm resistor. Then we've got our second combination, our 87.25 ohms. Hey, we can do some simple circuit analysis with this, right? So now we have what is this? This was V2. Yes, this is I2 equals V over R equals 0.2 divided by 97.25, which is equal to basically 2 milliamps. But there's an important question. That's supposed to say but. I just whatever. Bwee. How much current flows through R2? This is one of the problems with superposition. Okay, so here's what we have, right? If we come back to this simplified model, all right, let's go right back to the most complex model, okay? Take a look at that. What we just solved for is this current, I2. That's great. We know what this is. That is an important step. But how does that split out amongst this network? Right? So we've got to like unlayer the superposition and the circuit simplification. Like, this is not a straightforward way to solve this problem. There is an easier way, and next week we're going to run through exactly what that is. Because, you know, sure, we know this is 2 milliamps, but in order to know the effect on this circuit node over here, we need to know how much current splits this way and that way. So we need to leave this as 90.9 ohms and do the effective split. Okay, but now we need to split that current that's flowing this way between R1 and R2. So we've got to do 2 current divisions just for one voltage source's effect on that. And then likewise, right, we have to build this parallel combination for this whole network, solve for the total current, and then divide it out. And then we have to do that for this voltage source. And then if we add that all together, we will get the end effect on that node. There is a solution here, but we're not going to drive this all the way through because this isn't the right way to solve this problem. Remember the principle. I'm going to encourage you to solve this problem on your own. Take what we started and see if you can brute force your way through this superposition problem. Don't forget that when you're evaluating a particular voltage source, all other voltage sources become a short circuit, so 0 volts across them. All of the current sources become an open circuit, so there's no current flowing through them. And then we add the effects of all of these sources to come to the solution. Superposition is, quite honestly, a great circuit analysis tool. It is fantastic. It's a great tool to have in our quiver to add to our principles of series and parallel combination for resistors. Perhaps not finishing my own difficult circuit analysis problem is a little bit of a cop-out, but if you revolt in the comments, perhaps we will need to finish what we started today in the next one. Oh yes, If you finish up this problem, and I think it would be awesome if you did, make sure to share a picture of your work with us on Twitter or in our Slack channel, and drop a comment on this video with the answer. The voltage at V1 required to make node 1 equal to 1 volt. I'd love to see that. After all, doing something for yourself is a great way to make sure that you understand well, and it's almost as if that was the whole point. If you like this video and you can't wait for more, let me know by getting subscribed, hitting that like button, and leaving a comment down below. Coming up soon, we're going to be exploring Kirchoff's laws and dive into some more complex circuit networks. We're going to dive even deeper into this network to apply a theory known as nodal and mesh analysis. I can't wait. If you'd like to support the channel, don't forget to check out our Patreon page linked in the description. It really helps us out a lot, so thank you. Yes, seriously, thank you to everyone who has decided to become a Patreon member. You're a big part of keeping this all possible, and I'm just floored that you guys are chipping in the hat the way that you are. You're awesome. Most of all, I hope that y'all learned something great today, and I hope to see you again soon. So thanks for watching EEforEveryone, and thank you for staying till the end. Bye!